Have you ever wondered how your computer actually thinks? I mean, really, how does it make billions of decisions every single second, from finding a photo to, totally crushing you at chess? Well, the secret lies in these tiny microscopic switches called logic gates. Today, we're going to pull back the curtain and demystify that digital brain one simple rule at a time.
So, let's just start with that big question. How does a machine, a hunk of metal and silicon, like your phone or your laptop, actually make a decision? The answer, believe it or not, is shockingly simple. And it all starts with the language it speaks.
And that language? It's binary. I mean, everything your computer does, from showing you this very image to streaming your favorite show, gets crunched down into a massive, massive sequence of on and off signals. We just represent them as ones and zeros. It's the most basic language you can possibly imagine. So if you think of those ones and zeros as the nouns of this digital language, then logic gates are the verbs. They are the microscopic decision makers. They take in these binary signals, apply a very specific rule, and then spit out a new signal. They are, quite literally, the fundamental building blocks of every digital circuit you have ever used.
All right, so here's the game plan. First, we'll meet the basic building blocks. Then, we'll get to know their extended family. After that, we'll actually use them to build a simple circuit. And finally, we'll look at the real-world design challenges that engineers have to tackle every single day.
Okay, let's dive right in. First up, you've got to meet the three most fundamental gates in the entire digital universe: and, or, and not. Seriously, these three are the foundation for everything that comes next.
Kicking things off, we've got the AND gate. The easiest way to think about this one: imagine a high-security vault that needs two keys turned at the exact same time to open. Its rule is simple: both or nothing. Both of its inputs have to be on for its output to turn on.
And this little cheat sheet, the truth table, it lays it all out for us. You see, if input A is off and B is off, the output is off. If one is on but the other's off, still off. It's only right here, on this last line, when both A and B are on, that the output finally flips to on. That's the both or nothing rule in action.
All right, next on our list is the OR gate. Now this one's a little more laid back. It follows the any is enough rule. Think of a hallway light that has a switch at both ends. If one switch is on, or the other switch is on, boom, the light comes on. Just look at the difference in its truth table. The output, Q, is on if A is on, or if B is on, or even if they're both on. The only way it stays off is if both of the inputs are off. See? Any is enough. And last but not least for our basic trio, we have the simplest of the bunch, the NOT gate. This one is just opposite day. That's its whole deal. It's also called an inverter because whatever you put in, it gives you the exact opposite back out. It's super simple, just one input, one output. The truth table really couldn't be any simpler. Is the input a 0? The output is a 1. Is the input a 1? Then the output's a 0. Yep, that's literally it. It just flips the signal. It sounds simple, but trust me, this little guy is incredibly powerful. So, let's just boil it down one more time. The AND gate is exclusive. It needs all inputs to be true. The OR gate, on the other hand, is inclusive. It only needs any input to be true. This one single distinction is pretty much the foundation of almost all digital logic. Okay, now that we've got the basics down, this is where things start to get really cool. We can actually combine these simple gates to create a whole extended family that's way more powerful and efficient. So, meet the powerful cousins, NAND, NOR, and XOR. A NAND gate is just a not AND gate. It does the exact opposite of an AND gate. A NOR gate is a not OR, you guessed it, does the opposite of an OR. In fact, NAND and NOR gates are so powerful, they're called universal gates because you can build any other gate just by combining them. And then there's this special one, XOR, the exclusive OR. It's true if one input is on or the other is on, but not if both are. And you really don't want to underestimate that XOR gate. Its unique one or the other but not both rule is exactly what makes it the fundamental building block for binary addition. That means every single calculation your computer makes, from a simple spreadsheet to a complex video game, relies on this very gate. So we've got all these individual parts. How do we actually use them to solve a problem? Well, let's put them together and build a simple circuit that has a single unified goal.
Okay, here's our design challenge. We want a light to turn on, but, and here's the catch, only if one of two switches is on. If both switches are on or both are off, that light needs to stay off. So, Which gate do you think we need?
So here's how an engineer would think this through. First, you clearly define the exact output you want. Then, you figure out the logic you need to get there. From that logic, you choose the perfect gate for the job, you connect your inputs, and then you test it.
And the solution is a single XOR gate. That's it. Remember its rule? One or the other, but not both. It perfectly matches the requirements of our challenge. It's just a simple, elegant, and super effective solution.
Of course, in the real world, it's not always that simple. It's not just about getting the logic right. When you're designing something like a brand new processor, you have to balance some very serious and often competing priorities.
And this leads to this constant balancing act. Do you go for pure, raw speed, even if it absolutely destroys the battery? Or do you prioritize low power consumption for a device that needs to last all day? And maybe most importantly, can your design even be scaled up for more complex jobs down the road? This chart shows that trade-off perfectly. You've got Design A, which is an absolute speed demon, but just look at how much power it hogs. Then there's Design B. It's a bit slower, yeah, but it's way more efficient, which would be perfect for something like a smartwatch. There's almost never one best answer. It's always about picking the right tool for the right job. So why does all this matter so much? Why obsess over these trade-offs? Because a modern processor, like the one in your computer right now, has over 100 billion of these gates. A tiny, tiny inefficiency in just one gate, when you multiply it by 100 billion, becomes a massive heat and power problem. At that kind of scale, efficiency isn't just a nice-to-have, it's everything.
So, we'll leave you with a final thought. Logic gates are all about rules and conditions. So if you were a circuit, what would your rules be? If I got 8 hours of sleep and the coffee is ready, then my day is productive. What would the logic circuit for your perfect day actually look like? Thanks for tuning in.